Okay. Now the important point is, once you know these reduced density matrices, yeah, so you can basically determine any quantity or any observable of practical interest. Yeah, so once you know these, you know everything about these quantum quenches in the setup I have described. Okay, so now the equations of motion for these reduced density matrices simply follow from the equation of motion of this density matrix itself. So namely, so if you take the time derivative of the left-hand side here, the only time-dependent part here on the right-hand side is the density matrix itself. Yeah, so you get here dt rho, but that's just the commutator. Yeah, so you can write it like this. And then using cyclicity of the trace, you can rewrite this as the expectation value, so to trace over your time-dependent density matrix of the commutator of this product of creation annihilation operators with the Hamiltonian. Yeah, and the Hamiltonian again was written here. Yeah, and this commutator now you can easily work out using these canonical anti-commutation relations. So that's completely straightforward, and that gives you this celebrated BBGKY hierarchy. So really quite simple. Yeah. So what it is the time derivative of the nth reduced density matrix gives you a term that's proportional to the nth, to the n particle reduced density matrix. And you act on this with some differential operator, and the differential operator is nothing but the Hamiltonian in first quantization. So this object here, yeah, once as a function of x and once as a function of y. So that comes from the commutator structure. And then there is an additional piece, yeah, which comes from the fact when you work out the commutator here, yeah, you get something which will not be of the form psi dagger, psi dagger, psi dagger, psi dagger, psi, 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 psi. So you have to reorder basically some of the psis and psi daggers. So therefore you get interaction terms both in here and in here. And the second part in the commutator that you get now involves the density matrix, the n plus first density matrix. And that's also easy to see because here you have n creation and annihilation operators. In the interaction term here, you have two creation, two annihilation operators. And if you calculate this commutator, you will get n plus one creation operator, n plus one annihilation operators. Yeah, and this gives you something like this. Okay, so now
the way you defined the reduced density matrices, are these also equivalent to doing some partial trace over some region, or are these just unrelated?
Yeah, so the concept is exactly the same, if you wish. Yeah, so you see, it would correspond. Okay, so these reduced density matrices in particle space defined here, so they depend on coordinates x and y. Yeah, and if you constrain x and y now to be in part of your system, some particular subsystem, yeah, then this would correspond to a particular element of the reduced density matrix in the sense you have just mentioned.
All right, okay. Thanks.
Does that answer your question?
Yeah.
Okay, thanks. So it's just a different.
Sorry, can I ask as well, really quick? What does little n refer to? Sorry.
Yeah, so n basically just refers to how many of these psi daggers you have and how many of the psis you have. Yeah, so for example, row 1 would be just trace row psi dagger of x1, psi of y1. Yeah, So that would be the single particle Green's function. Yeah, and rho 2 would be trace rho of t, psi dagger, psi, psi, and so on and so forth. Yeah, and this Bogoliubov hierarchy basically connects these different reduced density matrices. So it's an infinite hierarchy. Yeah, because if you take the time derivative of the nth reduced density matrices, you get a term here on the right-hand side, which is the n plus first reduced density matrix. Yeah. But in principle, if you could solve this hierarchy, that would provide a complete description of the dynamics. But in practice, because it's an infinite hierarchy for these increasingly complicated objects, it's not useful. So in order to get something useful, you have to somehow truncate it to end up with a finite number of such equations. And the most prominent truncation scheme, that is called the quantum Boltzmann equation, and that's what we're going to discuss next. But before I do so, are there further questions?
Yes. I have a question.
Go ahead.
I noticed that the trace and the psi you have there is in second quantization, but then you input the first quantization Hamiltonian. Why is that?
Yeah, okay, so that's just a notation if you wish, because you see, what happens if you put your second quantized Hamiltonian here, you can calculate the commutator. Yeah, the commutator will give you, if you just work it out, yeah, so some differential operator acting on the reduced density matrix. And that differential operator, you can simply write, it turns out, in the form of this first quantized Hamiltonian. Yeah. So in other words, if you go to second quantization, I have written the Hamiltonian here in momentum space. But if I write the kinetic energy in position space, this would be psi dagger of x dx squared psi of x. Yeah, so that's what I would get for the kinetic energy if I write it in terms of the position space operators. Yeah, and now if you calculate the commutator of these with this psi dagger dx squared psi, yeah, you will end up with something that in the end is a dx1 squared or something like this. Yeah, can you see that? Or do you want me to? Okay. So let me try again to work this out. Share screen. It's not broadcast. Yeah. So what I'm using there is basically, let's look at something simple. So you have psi dagger of x, of x1, psi of y1. And here, let's just look at the kinetic energy. So here you would have, it would look in second quantization like this. So dx psi dagger of x minus dx squared over 2m psi of x. Yeah, so you would have something like this. Yeah, and now, okay, so what is this? You write it as dx. Yeah, and then here you get the commutator, psi dagger of x1, psi of y1. And here you would have psi dagger of x. So let's say 1 over 2m dx squared minus psi of x. Yeah. And now you basically just calculate this commutator. So you get a non-trivial contribution here from the, okay, so what is this? So this is psi dagger of x1. Here you get the anti-commutator, psi of y1, psi dagger x dx squared psi of x. Yeah, and then plus other terms. Yeah, but you see this is basically something like a delta function in second quantization. So this is delta y1 minus x. Yeah. And then what you can do is you can carry out the x integration. So this gives you a term which is 1 minus 1 over 2m. And then you would have one contribution, which would be psi dagger of x1 dy1 squared psi of y1. Yeah. So that is the calculation. And let's stop. If we go back to this, so that's one of the terms that arises here. Yeah, because in the first quantized Hamiltonian, you have precisely this dx1 squared over 2m or dy1 squared over 2m. Yeah, and you see that's precisely one of the terms that is present here. Okay, I hope that answers the question.
Thank you.
Okay. Okay, so now let's move on. Yes.
So previously, you said if we go back one slide, you said the reduced density matrix defined here is the same as the matrix element of the reduced density matrix defined by partial trace. But I think they are not exactly the same, because here we are taking a trace over all states in the many-body field.
Yeah, but you see what I said before, yes, is a very good question. But so I said this in words, but so let me come back to stop share. So let's see, share content screen. Okay, let me come back to this. So you see, I said it in words, but let me put some equations. So what you were saying is when you do a reduced density matrix, it's what in space you basically want to do. So let's say you have your one-dimensional system, and then you want to pick out some subsystem, call it A, and the rest.
Screen's not sharing.
Oh, sorry. Screen is not sharing. So let's see. Okay, now it's sharing, yeah. Sorry about this. Yeah, okay, so here I've drawn this thing. Let's say here is our system. Yeah, and then when you talk about reduced density matrix, you're used to picking out some subsystem. Let's call this A, and then you say the reduced density matrix of row A is the trace over B row, where row is the whole density matrix. Yeah. So now this is an operator that acts non-trivially only on this subsystem A. Yeah, and the matrix elements, I mean, so now if you look at something like trace row A, you can look at psi dagger of x1, psi of y1, where x1, y1 are in A. That would be a particular, let's say, matrix element of this reduced density matrix.
Sorry, but what do you mean by matrix element?
Yeah, you see, this, okay, so it's a little bit easier to write it for spin chains. So because everything is discrete. So let's just do the same thing for a lattice model of spins, okay? So then the way to write this row A is basically as the most general operator that can act on A. So this would be sigma, let's say 1, alpha 1, sigma L alpha L. So let's just take A to be the interval from side 1 to side L. Yeah. And then here you sum over alpha 1 to alpha L, runs from, let's say, 1 to 4. And then here you have some coefficients, alpha 1 to alpha L, or let's say from 0 to 3, where sigma J0 you define just as the identity operator, and sigma J1 would be sigma X on the side J, and so on and so forth. Yeah, and here is some normalization constant, so something like this. So this is what the reduced density matrix looks like for a lattice spin model. Okay, and now what I'm saying is these guys, yeah, are precisely the objects that I'm defining. Because if you take trace rho A of sigma 1 alpha 1, sigma L alpha L, well, up to some normalization, yeah, this is proportional to F alpha 1 to alpha L. Okay, and you see, this is the kind of thing that I have defined for you, but now not in the lattice, but in the continuum. Yeah, because
but I think in the case of particles instead of spins, I think it appears to me you are using a different definition of matrix element than what people usually use. Because if you replace the trace by just the zero state in the fork basis, then I think that is the matrix element in the usual definition.
well, okay. I mean, let's perhaps come back to this after the lecture ends. I'm happy to discuss more details. But so the definitions I'm using here for reduced matrix elements for the BBGKY hierarchy, those are the standard definitions, yeah, and they're related to reduced density matrix. Let's say that Anusha might have defined for you for spin models in this fashion. Okay.
Okay, thanks.
Yeah.
Just one question, just to orient myself.
Yes.
What you've defined as this rho n sub x and y, these are just n particle correlators, right?
Exactly. Yes.
And yeah, these are just correlators, and then I can interpret them as entirely parameterizing the reduced density matrix, provided all my arguments are within the cut.
Precisely. Yeah.
Okay.
That's precisely what I'm trying to say. Yeah. Okay, but let's move on because we have quite a lot to cover. So the main thing I wanted to say here is this is a hierarchy, yeah, because n is 1, 2, 3, 4, 5, 6, 7, all the way up to infinity, right? So you'll never be able to solve this system of equations in a closed form. So in order to get a theory of something, you have to truncate this. And there's a huge literature and industry about how to truncate this Bogoliubov hierarchy. And the most prominent truncation scheme is this quantum Boltzmann equation. And I'm going to sketch for you, and I stress sketch, how this is derived from the Bogoliubov hierarchy. And I'm following some paper by Salmhofer and Yao from 2004. So it's convenient to work in momentum space rather than position space. So to work with these reduced density matrices defined in this way, yeah, and they are obtained from these ones here simply by going to Fourier space. Yeah, so that's an exactly equivalent set of equations and set of reduced density matrices. And you can write this BBGKY hierarchy in momentum space. Yeah, and so it takes the form shown here. So the time derivative of the single particle Green's function has a piece which is proportional to the single particle Green's function, but then also a sum, yeah, which comes from the interaction term, that involves all of the two-particle reduced density matrices. And then the time derivative of the two-particle reduced density matrix involves a piece which is proportional to the two-particle reduced density matrix. But then also a piece from the interaction term that is proportional to all the other two-particle reduced density matrices, and then a piece from the interaction term that's proportional to these three-particle reduced density matrices. Yeah, and so this piece here in particular just corresponds to what you have here, and this piece here is what you have here. Yeah, so that's just a rewrite. And these kernels here, so these functions K1, K2, K3, so they are known functions. You can easily write them down, but it's not really important for what I want to say. I just want to sketch this. They are known functions of this interaction between your fermions. Okay. Now, in order to get this some closed set of equations, you follow through a few actually fairly straightforward steps. The first step is you take this equation here, yeah, and you integrate it in time, yeah. So you just integrate it here in time from 0 to t on the left-hand side and on the right-hand side. So that gives you something like this, yeah. Okay, so no big deal. Now what you can do is you can take this, or more precisely the right-hand side, and substitute it back in here, yeah, in the equation for row 1. Okay. No problem. Now comes the important step. Now you make an assumption, and the assumption is that the so-called connected correlators are negligible. And connected correlators are essentially defined in this way. So this two-particle reduced density matrix can be written as a connected part, yeah, plus certain products or sums of products of the single particle reduced density matrices. Yeah, and the three-particle reduced density matrix also will have a piece that involves only products of single particle reduced density matrices. So this denotes some antisymmetrization in these momenta, and then plus other pieces, but they always involve connected correlations, and these connected correlations are assumed to be small. Yeah. Okay. So once you do that, you will get an equation that only involves this single particle Green's functions, nothing else. Okay, it takes this form here. Yeah, so you now get different orders in the interaction potential, which has this small parameter, which is lambda. So you get a first order piece, which is like so it's quadratic, and then you get second order pieces. Yeah, one which involves two of these single particle Green's functions, and one which involves three. Okay. Now, this is now a closed set of, or a closed evolution equation for this single particle Green's function. And this particular equation is called the second Born approximation. And the only thing to take away here is if you're given some initial conditions, so this single particle Green's function, or the first reduced density matrix, so this row 1 at time t equal to 0, you can integrate this over time and get this reduced density matrix at all later times. Yeah, so this is now useful. So you certainly can do this numerically on the computer. Now, there is one important thing to note. this reduced density matrix time t depends on all reduced density matrices at earlier times. So we say this is not Markovian, so because it depends on the history of the system from time t equal to 0 all the way up to time t. Yeah, so this is what you what this time integration here signifies. Okay. Now, in order to proceed, what you do now is you first take the infinite volume limit to remove some potential complications, and you define what's called a Wigner function, which is a partial Fourier transform of this reduced density matrix. Yeah, so this is just a definition. It's a function which has precisely the same physical content, precisely the same information as this single particle Green's function, because it's obtained just by this Fourier transform here. Now, this is a useful object because it has a rather nice physical interpretation. And that physical interpretation is as follows. So if your quantum state, your time evolving quantum state, yeah, so it's described by this full density matrix rho of t, is slowly varying in space. Yeah, so it's almost constant over big patches, and moreover has a finite correlation length, which means that if you calculate these reduced density matrices here, they will decay exponentially in the various distances here. So x1 minus y1, x1 minus y2, and so on and so forth, if the separation between these coordinates becomes large. So that's what a finite correlation length means. That basically means different regions of your system are extremely weakly correlated. Yeah, so you have strong correlations only within a finite radius, and outside you're not correlated anymore. So if you have this finite correlation length, you can think of this density matrix if it's slowly varying in the following way. So here is some spatial coordinate, here is some position x, and here is some time axis. So if it's slowly varying in space and has a finite correlation length, this density matrix, then you can take some patch in space, which I call AX. And in that patch, within that patch, this quantum mechanical state is for all practical purposes homogeneous. Yeah, so translationally invariant diffuse, so homogeneous. Yeah, and in that case, this Wigner function defined in this way is to a very good approximation equal to the momentum distribution of fermions with momentum p defined on that patch. Yeah. So what this Wigner function is physically, we say it's a quasi-probability distribution of fermions with momentum p in a cell centered around position x at time t. Okay, so those are the words, and what it means in practice is this. So was that comprehensible, or are there questions about what this Wigner function is? Mm-hmm. Okay, so nobody asked questions, so then let me carry on. So now this we will come back to later. So now, because
just one question, yes, about just where you did the unrelated to the Wigner function, but about the truncation.
Yes.
Yeah. So you've only taken the first sort of two reduced density matrices to get for this truncation. So
you mean here? Order. Yes.
Yeah.
Yes.
So in
that's
principle,
a very good question.
If you like in principle, you would just repeat this procedure that you did for 2 if you wanted to go to higher order, say.
That's absolutely correct. So you could repeat it, but you see, this will be organized by different powers of this small parameter lambda.
Right.
So to order lambda squared, this is all I have.
Right.
And if I were to do what you're saying is I would get terms which are lambda cubed, lambda to the 4th, and so on and so forth. But you could do that, and that would be different truncation schemes.
Right. Okay.
Yeah. And as I said, so this is the simplest one.
All right. Yeah. Thanks.
Okay.
One follow-up question on that.
Yes.
I just noticed the orders of lambda. So here we took row 2 and row 3, but truncating them gave me the same effect at a power of lambda. I still have lambda square power for both of them.
Yes.
So when you said that I could take further orders, would I get terms in lambda square as well? Which means that if I were to just look at lambda as my small parameter, if I have to do something very consistent, I would have to go to all orders.
So what you would get if you go to higher orders, you would get an extra contribution, let's say, which is quadratic in these row 1s, yeah, but which would be proportional to lambda cubed.
Right, right.
Yeah. And you would get something which is cubic, which would be proportional to lambda cubed or lambda to the 4th, and so on and so forth. But these would correspond to more to different truncation schemes. And as I said, I want to stick to the simplest one, which is the Boltzmann.
No, fair. What I didn't understand is right now M3 has a lambda square power as well. If I write down a term with an M4, will I get a lambda square contribution?
No. To order
okay, that's all what I wanted to ask.
This is
okay. That's all I wanted to ask.
So,
okay,
so the corrections to this is lambda order lambda cubed.
Okay. Okay.
And it simply comes from the fact, so you can go back here and basically see this here. You see there is a lambda order lambda here already.
Mm-hmm.
Yeah. And then from the equation for row 2, you get an extra lambda.
Right.
Yeah?
Right.
And now if you do the row 3, yeah,
mm-hmm.
so you would have to integrate it and substitute it in here.
Right.
Yeah,
I'll
then
push
you
up
would
my
get an order lambda squared, order lambda cubed.
Okay. Makes sense.
Yeah.
Makes sense.
And
in this entire and in this entire procedure, we're not doing anything like self-consistency where we're coming back to look at the connected correlator, which we ignored.
Yeah, so the connected correlator is ignored here. Yeah, so in principle, you could check whether this is a consistent approximation by also writing a scheme like this for row 2 and just checking whether it's really small. Yeah.
Okay.
But
sure.
this takes us beyond what.
Okay. Fine. Okay. Thank you.
Okay. Great. Okay, so now let's come back to this.
Let me maybe still ask a question relating to the Wigner function.
Yes.
So is there any particularly simple reason for why this specific Fourier transformation, such that we then get this probability distribution?
Yeah, it's a simple calculation. You can actually show under this assumption that this quantum mechanical state varies slowly in space and has a finite correlation length. You can take this definition and show, yeah, that this Wigner function reduces precisely to this kind of mode occupation number on the patch. Yeah, it's an actual calculation. And if you chose something else here, you wouldn't get this.
Okay, and so that's also the reason why we choose this form.
Precisely, yeah.
Okay.
So it has a very nice physical interpretation. Yeah.
Okay, thanks.
And it will be very important.
I also have a question.
Yeah.
So in the previous slide, can you remind me what is Poisson-Dagger AXP, the next slide?
Yeah. So these ones here, so this would be momentum space fermion operators, but defined only on the patch. You basically take the Fourier transform of the psi of x, but only on the patch.
I see. Thank you.
Yeah. Okay, so now this Wigner function fulfills an equation very similar to the second Born approximation. It's just obtained by taking this partial Fourier transform. And then the final step is now you take the so-called Boltzmann scaling limit. So you consider late times, yeah, and large values of x and weak interactions, yeah, such that the distance x over some scale, which you take to infinity, is held constant, and the time t over some large scale is kept constant, and the interaction strength lambda is scaled to 0 in this fashion, yeah, when lambda becomes large. And the reason for taking this scaling limit is because then you get rid of this retardation effect. So this T prime integration disappears. Yeah? And what you end up with is the so-called quantum Boltzmann equation for the limit, yeah, in the scaling limit of this Wigner function, which is defined here. Yeah, and so this quantum Boltzmann equation is just an equation for this Wigner function. Yeah, so you have two terms which are linear in the Wigner function, and then you have terms here on the right-hand side. It's called the collision integral, which are quadratic and cubic in this Wigner function. So this is a nonlinear evolution equation for the Wigner function. It's much simpler than what we had before, because there's no time integration anymore involved. Yeah, so this is the quantum Boltzmann equation, and I want to make some comments. So the rationale for taking this particular scaling limit is it's believed that this quantum Boltzmann equation is in fact exact in the scaling limit. It's not an approximation. Now, to prove this is ongoing research in mathematical physics. So people are trying to prove this mathematically. Now, as a physicist, we don't use it really in the scaling limit, which quite artificial. So we use it instead for large x and t and small lambda. Yeah, and there it's not exact, but it's often a very good approximation. And its advantage is it's easy, it can be readily solved numerically. And what it gives you, if you use it in this large x, large t, large small lambda limit, it gives you an approximate value for this Wigner function, and therefore the first reduced density matrix. And because you have made the assumption that the second reduced density matrix, third reduced density matrix don't have connected pieces, so they are given just in terms of this one, it gives you basically all of these reduced density matrices. So it gives you, in other words, a complete description of the dynamics. And the final caveat, okay, so this quantum Boltzmann equation, it's clear from this derivation, doesn't apply at short times. And so therefore what you have to use to do in practice, so you have to basically start integrating this equation for some time, and then eventually get some initial condition for the Boltzmann equation, and then integrate the Boltzmann equation. Okay. So that's the quantum Boltzmann equation. So I've gone a bit fast, but I have a fair bit to cover. So let me perhaps go on because time is disappearing fast. So now, what happens at very late times in large scales? So Anusha already discussed this in her lecture. So what happens there is the system equilibrates locally. So if you look at some small patch or some large patch of the system at late times and large scales, it locally looks like, let's say, a thermostat in a generic system, or generalized Gibbs ensemble if you have additional conservation laws. and I think Anusha covered this, importantly, these the local physics is fully characterized by the conserved quantities. So let's say the energy, particle number, momentum in a generic system. And the dynamics then at late times and large scales is characterized by diffusive transport of the conserved quantities. And that's described by hydrodynamics. And that arises as follows. So you have some globally conserved quantities, energy, particle number, or momentum. So these are operators that commute with the Hamiltonian, and you can now define their local densities by just taking the density of these operators, which are local or quasi-local, and taking their expectation in your quantum mechanical state. And because they are conserved quantities, this gives rise to continuity equations. Yeah, so the time derivative of this density of the expectation value of the density of the conserved quantity is minus the divergence of some current that carries this conserved quantity away from your patch. Okay, so this basically just tells you you're looking at the density of some conserved quantity. Now, this local equilibration here basically means everything, and in particular, this density of the currents is entirely determined by the density of the conserved quantity in your patch, because the system is locally in equilibrium. And that means you can now rewrite the right-hand side here in terms of these densities of the conserved charges, just using the chain rule. Yeah, so the time derivative of the expectation value of the density of the current can be expressed in this way. So here you get some matrix of derivatives, and what you then do is you diagonalize this matrix. Yeah, so you do a similarity transformation to make it diagonal, and then you change variables from these expectation values of the densities of the conserved charges to new variables, which are defined here through this similarity transformation that diagonalizes this matrix A. And this gives rise to hydrodynamic equations of this kind, which basically tells you how in these coordinates, if you wish, the densities of conserved quantities are being transported in your system. Okay, so that basically tells you what happens at very late times and large scales. And the difficulty in general is how to determine these velocities here. Yeah, so that tells you how far you move these densities of conserved charges.
Fabian, there appears to be a raised hand by Saranya Moitra.
So I can't see that. Yeah.
Okay. Now, right at when you were introducing this, where you have this diamond over here, you mentioned over here that there is always diffusive transport of conserved quantities, but then later when you're deriving things, I don't necessarily see why it should always be diffusive, because you have so you have this del of J, and if I have something like a Fourier law for J, then I can easily see it's diffusive. But then if I have these velocities involved, then is it a general expectation that it could be diffusive still?
It's an expectation, yeah, and for a generic system, so to speak, yeah. So where you just have few conservation laws, so the general expectation it's diffusive. And as I was about to say, so you can investigate this, for example, by using the quantum Boltzmann equation, yeah, to work this out, yeah. But you're right. I mean, so this is, an expectation. I mean, so one should investigate.
No, I just didn't see. If I see a velocity, I think something like ballistic. Maybe that's a naive question.
Not here. Yeah. So it's really diffusive.
Thank you.
Okay. So let's see. Right. Okay, so this is what happens in generic models. So now what happens in these integral models is very different. And so let me, in the remaining 10 minutes or so, explain a little bit what happens there. So for simplicity, let's just look at free fermions, which is the simplest integrable Hamiltonian. And let's also take the dispersion of these free fermions just to be p squared. Yeah. So what happens there at late times and large scales, we have already worked out. Yeah, because when we kind of derived or sketched the derivation of the Boltzmann equation, all we have to do in order to deal with free fermions, we have to set lambda, the interaction potential, to 0. So that gives us then this evolution equation for the Wigner function, just from what we had done before. And this looks like these hydrodynamic equations I just motivated in the general case, with two important differences. The velocity, the characteristic velocity that enters here, is the group velocity of the free fermions, of the stable particles. And rather than having hydrodynamic equations for, let's say, 3 densities, yeah, which corresponds to energy, momentum, and particle, we get this equation for the Wigner function, which is a function that depends on momentum. Yeah, and now in the thermodynamic limit, this basically would correspond to an infinite number of modes, because your particle basically can carry any momentum. Yeah, so it looks like hydrodynamics, but a weird one. And that's relatively easy to understand simply by noting these free fermions actually don't have 3 conservation laws, but in the thermodynamic limit, they have infinitely many conservation laws. Yeah, because all of these quantities here are in fact conserved. They commute with a Hamiltonian. It's very easy to see because they're just proportional to the mode occupation number, as is the Hamiltonian. So these clearly commute. And you can also easily convince yourself the densities of these conservation laws are in fact local. Yeah, so you can work out what they are. So the density can be written as an integral over an nth derivative of a delta function times psi dagger psi. And if you write this, it basically just involves the creation annihilation operators in x at position x and derivatives, n derivatives. Okay, so now in order to go from here to this hydrodynamics, what you do is you observe that these conservation laws can be combined or can be obtained from a generating function. And that generating function I call a Wigner operator. It's just this operator written here, which is very closely related to this Wigner function we defined earlier. And the time evolution of this operator defined in this way follows from the Heisenberg equation of motion. Yeah, so it's just given by this equation here. And because this Wigner operator is basically the generating function for these Qn of x's, this is in one-to-one correspondence with continuity equations for all of these charges. And then once you take the expectation value of this operatorial equation here, you get a equation for the Wigner function. Yeah, and that's precisely this generalized hydrodynamics in its simplest case. Yeah, so in other words, for free fermions, you have like hydrodynamics, but precisely in this way, so that the normal mode velocity is group velocity of stable particles, and you get hydrodynamics for a function, yeah, which is some kind of generalized mode occupation function. Yeah, and I should note in this little derivation I've just done here, it's a little bit atypical because I didn't have to take really this late time, late space limit in order to get this hydrodynamic equation. And this is just an artifact of the fact that my dispersion was simply quadratic, p squared. So in general, you have to go back to this limit that we introduced for the Boltzmann, quantum Boltzmann equation, and get precisely back this hydrodynamic equation for the Wigner function. And that's easy to solve given initial equation, some initial conditions. Okay, and so in the last 3 minutes or so, let me just tell you how this generalizes to interacting integrable models. So now I add my interactions back. And then what you can do is you can, just by brute force, essentially construct an extensive number of local or quasi-local conserved charges by adding additional pieces here. Yeah, so you start with the free fermions, and now you add something which is quartic, something which is sextic, something which is optic, and so on and so forth. And you can work out what these are order by order in this small parameter. And interestingly, you can do this for any interaction potential and obtain a continuity equation. Okay, so now what does that mean? Does that mean in any model I have infinitely many conservation laws? Well, not really, because these charges constructed in this way are generally non-local. Yeah, so they don't have any good locality properties, and therefore are not important for physics, which is based on local equilibration. And you can show they become quasi-local only in very special choices of this interaction potential. And these precisely correspond to integrable models. And okay, so you can show you precisely recover all the known integrable models by this procedure. And now what you do is you just mimic what we just had for free fermions. So you introduce a generating function for the density of conserved charges. You can do this again explicitly, and you do the same for the currents. And these generating functions then fulfill some continuity equation that just follows from the Heisenberg equation of motion. That's again very simple. And finally, you take an expectation value and obtain a generalization of this Wigner function in the interacting case, which you now can write in terms of these reduced density matrices in this BBGKY hierarchy. So the leading term is just the Wigner function, but now you get additional pieces, yeah, which involve the 2-particle reduced density matrix, the 3-particle reduced density matrix, the 4-particle reduced density matrix, and so on and so forth. And you can work out these kernels here order by order in perturbation theory. And so this generalization of the Wigner function has a completely analogous physical interpretation. It's now the momentum space density, not of free fermions, but of stable quasi-particle excitations that exist in these interacting integrable models. And now there's one crucial difference between interacting and free theories, and that is that the properties of the stable particles, stable excitations, now depend on this distribution function itself. Yeah, so on the local equilibrium state, yeah, that you have, and in particular, their group velocity now is a functional of this Wigner operator. This generalized Wigner function itself. Okay, and then the final step is, and I'm almost out of time, which is just as well. You again go to this limit where you take x to infinity, t to infinity, x over t fixed, and assuming again the system equilibrates locally, you obtain now a hydrodynamic equation for this object here. Yeah, so this generalized Wigner function. And so this evolution equation here, that is called generalized hydrodynamics. And that is the theory that describes, for example, these experiments that I started with at the beginning, or some variant thereof, some modification thereof describes these experiments. So this is my final slide, and I have just a few comments. Now, it's important to point out there are very efficient methods to calculate these required group velocities exactly in these integral models, even for strong interactions. And these GHD equations, so these equations here, can be easily or readily integrated numerically. And this gives you results in the first instance for the expectation values of the conserved charges and currents, which are particular observables. But there are extensions, so many extensions exist. So you can extend this to certain other observables. You can look at what happens at earlier times, so not at this asymptotic late times, but what happens at shorter times, etc. So the field has been very active. And I have run out of time, so I close here. So thank you for your attention. And I apologize, I rushed through this in the end, but okay.
Okay, thanks a lot for covering this amount of material on that pedagogical level in such a short time. So we've had quite a few questions as we went along. Are there any other questions before we break?
Yeah, I was wondering, is there an analog of the H theorem, like in the classical Boltzmann, for this kind of thing?
You mean that entropy always increases, or so? What
exactly? Yes.
Yeah. So the analog in this many particle quantum setting is, if you wish, the von Neumann entropy increases as the system evolves in time. Yeah, and the von Neumann entropy is just defined as the trace over rho of t, or rho of t log rho of t. Yeah, so the entanglement entropy, if you wish. So the entanglement entropy of a subsystem, I should have said, so that increases in time.
Is it the trace of rho of t log rho of t, or rho 1 of t? Because
no, so it's over subsystem rho a of t log rho a of t, where a is some subsystem.
Okay, it doesn't have anything to do with like the different rows in the BBGKY hierarchy. It's not.
Yeah,
like
so not so easily, because these are elements of this reduced density matrix. But so the simple statement to make, and so this is known as the von Neumann entropy of a subsystem, the entanglement entropy of a subsystem, so that grows under non-equilibrium evolution.
Okay, thank you.
Yeah, so it's, yeah, sorry.
Okay, any other question?
I have one naive one. Sure, please go ahead.
Yeah, just one maybe clarification question. So when you're generalizing to this interacting integrable, so the generating function, sorry, so yeah, in the non-interacting case, did we have a generating function also for the current?
So in the particular, yes, in general, yes, but in this particularly simple case that I had covered here, the currents are actually proportional to some of the charges themselves.
I see.
Yeah. So in general, yes. Yeah, it's just for the p squared, for the p squared dispersion, the density of the currents are basically proportional to the qn plus 1.
I see. Okay.
It's just a fluke.
All right, thanks.
Okay, there was another question.
I had a very naive question. I mean, so far, whatever that has been covered, if I were to have some classical integrable model with many conserved quantities, would a priori, it seems like at least whatever you flashed right now, it would go through in principle. So, yeah, or I is it?
Yes. Mm-hmm.
So, I mean, where does the quantumness of the model would come in these equations? Yeah,
okay, so these equations, in a sense, they're hydrodynamic equations, so they look classical. I mean, so this is true.
Right.
Yeah. But the underlying physics is really quantum mechanical interference, many particle interference. So this emerges basically from dephasing. Yeah.
Right.
Quantum mechanical dephasing. So it's really inherently quantum mechanical, even though the evolution equations turn out to be classical in the end of the day, in this limit.
Okay. Okay. So would there be something? So, for example, when you do say saddle points or something in some theories, would there be like fluctuations around these?
Yes, I mean, so you can
control
study
ways of.
You can study this question. It's a very good. It's a very good question. So this is in its infancy. So at the moment, this is what we have. But so in principle, you can try to go beyond this. Yeah, and in some sense, you can think of this as some kind of saddle point solution, and now you can look at fluctuations around.
Okay.
Yeah,
Okay.
so this is indeed correct. Yeah.
I also have one question.
Go ahead.
First of all, I think I missed this towards the end, but since integrable models, the conserved charges of the integrable models are non-local, I didn't quite follow how how we were able to get the hydrodynamic equations from them.
Yeah, so they're not. They actually have good locality properties. So they're actually quasi-local in this integrable case. Yeah. So if you try to do this for a non-integrable models, they turn out to be non-local. So then you cannot get hydrodynamics from there.
Thank you.
Yeah, but in the integrable case, they precisely have these good locality properties, and that's the difference between integrable and non-integrable. So that separates the two classes.
Thanks so much.
Hello.
Yeah.
I have some questions. So I was wondering about the truncating reason before in the hierarchy.
Yes.
Is it connected to the Boltzmann scaling limit? And also,
no, so the truncation.
I think you mentioned something about excitations. I need some elaborations on that. Thank you.
Yeah, okay. So the truncation is not related to the Boltzmann scaling limit, right? So the truncation I did here by basically assume that connected correlators are negligible and then stopping here at second order, at order lambda squared. So that gave me a closed truncated set of equations. Okay. And I can truncate later. That gives me more complicated approximation schemes. So that's the approximation. The scaling limit is a different one. Yeah, in the scaling limit, you basically get rid of these time integrations. Yeah, and you end up with something that's Markovian. So this reduced density matrix at time t plus dt or delta t only depends on the reduced density matrix at time t. Yeah, and that's why the Boltzmann equation is so nice. Yeah. So there were these two steps, and then with these stable excitations, yeah. So I rushed over this. I mean, that's a characteristic property of integrable models. So for free fermions, you know this. You can actually consider a stated finite energy density, and they are stable particle Hall excitations around that state. It's just the same free fermions that you have around the ground state, if you wish. Yeah, and for interacting integral models, this picture generalizes. Yeah, if you have some stated finite energy density, you can excite stable excitations around that state. So stable means infinitely long-lived, and they don't decay because of the conservation laws. They stabilize them. So that's a characteristic property of integrable models.
Thank you.
Okay. If there are no further questions, we perhaps take the break now. So let's see you in 20 minutes. So that's noon Tallahassee, 9 o'clock San Francisco, or 6 p.m. Central Europe. And so let's thank Fabian very much again for a clear and action-packed lecture.
overly ambitious. Yes. Thank you.
All right. Thanks a lot.
Cheers. Yeah.